So we are heading towards the Holocene and the Anthropocene in terms of our discussion of climate variability and change over time. We are now up into the end of the last ice age, which happened, the glacial maximum reached 21,000 years ago when the warming started, and it kept warming with a little hiccup called the Younger Dryas that we talked about, and there was an older Dryas as well. And as usual, we don't have a consensus on exactly how it terminated, but obviously orbital forcing would have to play a role, and then internal feedbacks play a bigger role. And there was for some time some debate about whether there was a meteorite crash that caused the termination, because there was some evidence of a meteorite crash in Greenland, but more recently a paper came out saying that was much older and not towards the end of this last ice age. Okay, so let's take a nice summary of this paper talking about essential elements of a termination, summary of conditions and processes described in the text that contribute to termination of a late Pleistocene ice age. So it's not particularly about the very last one, but a general typology of ice age terminations. AMOC, of course, indicates Atlantic meridional overturning circulation. Very large and isostatically depressed northern hemisphere ice sheets with marine-based components. So when the glacier grows and gets very heavy, it pushes the land down, which we call isostatic depression. Rising northern hemisphere insolation leads to ice sheet melting and instabilities that deliver water and ice to the North Atlantic. So we are already edging towards the Atlantic meridional overturning under a depressed continent, which would make it, relatively sea level is higher. Reduced AMOC and spread of winter ice produce particularly long northern hemisphere stadials with severe winters. Okay, Asian monsoon weakens ITCZ, and the westerlies of both hemispheres shift eastward. So southward. Westerlies cannot shift eastward, southward. So you are talking about how the equator to pole temperature gradient and the whole jet streams and the entire meridional cell structure changes, which we haven't talked about in this course, but you can look it up in my other podcasts. Southward shift of the southern hemisphere westerlies and oceanic bipolar seesaw warm Antarctica and raise atmospheric CO2. So when both hemispheres westerlies shift southward, the northern one is coming down towards the equator, the southern one is going more towards the Antarctic continent. So there are changes in ocean circulation and air-sea CO2 exchanges. Prolonged effects of northern hemisphere stadials raise atmospheric CO2 above the threshold necessary to sustain interglacial conditions. So this is something that is just you can think of it as one of the hypotheses, but you can get obviously evidences for these sorts of things, which is why data drives these sorts of hypotheses, and then models tend to want to confirm or reject such hypotheses, test these hypotheses. So we're looking at CO2 and proxy global temperatures as an anomaly with respect to some base period with the Antarctic composite on this side. We are going from the last glacial maximum towards the Holocene. So the last glacial maximum here, cold temperatures, low CO2 as you remember, older Dryas, one hiccup that happened before the Younger Dryas here. So you can see that that's seen in Antarctic composite but not seen in the northern hemisphere proxy global temperature, or proxy global temperature, sorry. So you see the warming, rapid in Antarctic composite, not so rapid in the global temperature, and you have the cooling again, which was much more pronounced in the northern hemisphere. So there's bowling Alarod and younger dryas events there. Then we hit the Holocene, where temperatures have remained relatively uneventful compared to the changes during glacial, interglacial, and so on. So here we are looking at a frequency kind of thing, looking at lag years in temperatures leading CO2. So this is the southern hemisphere, and this is the northern hemisphere. Oops, why on earth are you doing this to me? So temperature lags CO2 here, and temperature leads CO2 here. So you can see that temperature southern hemisphere is leading here, and northern hemisphere is lagging in terms of CO2. So glacial, so if solar insolation orbital forcing is triggering deglaciation, then temperature will lead, but the CO2 response, depending on whether you are in the northern hemisphere or southern hemisphere, with large uncertainties, of course, you can begin to see how the two hemispheres are responding differently. And we have also talked about the bipolar seesaw operating at some time scale within that. So you always have to be able to separate low frequencies and high frequencies. Looking a little bit more, relative sea level obviously went from about 120 meters below the current levels to the current levels as the glaciers melted and all that water was released back. So looking again at global proxy temperatures, so this is the northern hemisphere ice sheet area. It's 100% when the sea level is at its minimum, and ice sheet has disappeared, even though there are glaciers on the northern hemisphere in Greenland and Antarctica, in the southern hemisphere, and mountain glaciers all over the world. Okay, so this we are only talking about ice sheets. CO2 again, which we saw going from about 160 ppm here to the end of the glaciation at about 235-40, and then we reached, of course, 280 by the time we got to industrial beginning of the industrial revolution. Model global temperatures, trying to figure out what are the various forcings that create this. So look at the insolation relative to the present in terms of percentages coming out of the last glacial maximum. It began to increase and reached its peak during the end of the glaciation into the Holocene, and there were associated monsoonal changes as well, greening of the Africa and so on. So the global annual is here, and at 65 south there is a corresponding change. Obviously they are not symmetric because of the obliquity and so on. Okay, well, because the distance from the sun, which is during the aphelion and the perihelion. Okay, these are proxy hemispheric temperatures. This is the same plot we are looking at, but now with details on the CO2 and model hemispheric temperatures, comparing the two. Proxy delta T here, contributions from various processes in the model. You can try to separate how various processes contribute to the end of glaciation. So big question, of course, is what was the role of AMOC? So you can see that AMOC was stronger here 22,000 years ago in terms of Sverdrups, and it decreased, and then it has slowly increased over this period. Again, looking here at other evidence, protactinium, thorium evidence for last glacial maximum, older Dryas, Bowling Allerod, Younger Dryas. So Bowling Allerod is this warm period, Younger Dryas. There's quick cooling again and coming back into the Holocene. In other words, models try to use various evidences to try to look at how things changed with different contributions. Okay, so this is looking at temperature trend in degrees C per kilo years, going again from 22,000 years to the middle of the Holocene in various latitude bands, and you can see that the northern hemisphere had the blips of Bowling Allerod and Younger Dryas much more clear. So if you look at the onset of the seesaw, there is still the bipolar seesaw, and onset of the CO2 increase. Okay, so the Greenland interglacial range. So northern hemisphere has had different evolution during the deglaciation coming into the Holocene than the southern bands, which is also important to remember. Obviously by this time Homo sapiens were all over, so it's a question of how they were interacting with the megafauna at the time, habitat suitability changes and extinctions of megafauna, and how human activity in terms of agriculture, deforestation and growth in population were beginning to affect the environment as well. Bill Ruddiman would argue that increase in CO2 already had human contribution from the beginning of the agricultural era. Okay, the Younger Dryas itself has had multiple stories. The most accepted or most stated one is that as the glaciers melted, Lake Agassiz filled up, but there was an ice bridge that had held the fresh water back, and the ice bridge broke at some point around 12,000 years ago and released large amounts of water. And there is a debate about whether this water really got released into the North Atlantic Labrador Sea region or went south into the Gulf of Mexico. But nonetheless, if that kind of people do model experiments to see how much water you would have to put, how much fresh water you would have to put in the North Atlantic to perturb the AMOC. They're called hosing experiments, and there are lots of hosing experiments done, but this goes into details about model sensitivity to freshwater freshening of the North Atlantic region, and they often tend to require much higher freshwater flux than can be inferred from the dam burst of the Lake Agassiz. Okay, so that's just a quick summary of how the termination of the last glacial happened and what processes were potentially involved. Of course, in addition to the initiation by the increase in solar radiation, you started having internal ice albedo feedbacks, and we know that the warming goes rapidly. Except for these blips of Younger Dryas, it did go fairly rapidly, and now of course we have to compare that to the warming since the pre-industrial revolution. There is no models generally tend to show that, and IPCC states this as well, that there is no expected collapse of the meridional overturning circulation in the 21st century, or maybe not even in the 22nd century. But of course, if there is an acceleration of glacier melts over Greenland and Antarctica, then you could have much more serious perturbation than what we are estimating based on model simulations. Okay, so we'll leave it there.